Next we prove the location root theorem. Location root theorem states that I is an interval closed interval AB, and let f is a function from I to R is a continuous function with the condition that f of 0 is less than 0 less than f of b, or f of a is greater than 0 greater than f of b. That is, if f is a continuous function satisfying any of these conditions, then there exists a point c in open interval ab such that f of c is equal to 0. Let us look into the graph of what is meant by this location root theorem. So this is location root theorem says that is I is an closed interval AB, and f is a function such that f of a is less than 0 and f of b is greater than 0. If f is satisfying the first condition, that is if it is f of a is less than 0 and f of b is greater than 0, then this condition, then there exists a point, then surely this curve surely passes through the x-axis one time. That is, this theorem is saying this curve, if f of a is less than 0 and f of b is greater than 0 in some closed interval ab, then the curve f of x surely cut the x-axis at some point. That point is c. Okay, that point is c, such that point is c such that f of c is equal to 0. Since it is in the x-axis, then f of c must be equal to 0. In a similar way, if f of a is greater than 0 and f of b is less than 0 also, this will happen. There exists a point c in x-axis such that f of c is equal to 0. What this means, that f of c equal to 0 means that c is the root of the function f of x equal to 0, or otherwise as root of the equation f of x equal to 0. So this is the location root theorem says about how we will find a root of the function if in a closed interval ab, if it satisfies this condition or this condition. That is, if f of a is less than 0 and f of b is greater than 0, then there exists a point c in between a and b, open interval a and b, such that f of c equal to 0. That means that c is the root of the function f of x, or c is the root of the equation f of x equal to 0. In a similar way, if f satisfies this condition, that is f of a is greater than 0 and f of b is less than 0, then also there exists a c such that f of c equal to 0. Then also c is the root of the equation f of x equal to 0. This is the location root theorem. We are locating where is the root of the function f of x. For that we need two conditions. F must be continuous function, and also if f is a continuous function on closed interval ab, and if it satisfies any of these conditions, that is f of a is less than 0 less than f of b, or f of a is greater than 0 greater than f of b, then there exists a root in open ab such that f of c equal to 0. If this is a root, then this condition will satisfy automatically, that is f of c equal to 0 when c is the root of the equation. So location root theorem, as its name says, it is locating the root of the function, not just a function, root of the continuous functions on an interval closed interval ab. It is defined on a closed interval ab. So location root theorem locate the root of the continuous function. Okay. So we will prove this theorem using some construction of some successive intervals, and using that we will prove this theorem. So we have an interval proof. So we have an interval I which is closed interval AB, we are taking I as I1, that is I equal to I1 as A1 B1. Okay, so first we have the interval A1 B1, which is same as AB. Okay, we are just renaming A1 as A and B1 as B. Okay, so for this interval we can find out the midpoint. Okay, and also this function also this function f satisfying the condition, first condition, we are taking this f of a less than 0 less than f of b, that is f of a is less than 0 and f of b is greater than 0. Here it is f of a is less than 0 and f of b is greater than b1, sorry, b1 is greater than 0. F of a1 is less than 0 and f of b1 is greater than 0. Surely this is a closed and bounded interval. We can find out the midpoint p1 as, and name it as p1, p1 as a1 plus b1 by 2. It is the midpoint of the interval. Okay, so we are trying to find what is f of p1. F of p1 has three choices, that is f of p1 may be equal to 0, or f of p1 is greater than 0, or f of p1 is less than 0. Okay, if f of p1 is equal to 0, then we want this some c according to our theorem. If this condition satisfies, we want some c such that f of c equal to 0. So if f of p1 equal to 0, we can take c as p1 and we have proved, the proof is enough for c equal to p1. When c equal to p1, our proof terminates. Okay, but if f of p1 is greater than 0, but if f of p1 is greater than 0, or f of p1 is less than 0, that means if f of p1 is not equal to 0, then these two conditions will satisfy, either one, that is f of p1 is greater than 0 or f of p1 is less than 0. Okay, so if f of p1 is greater than 0, if f of p1 is greater than 0, we take another, we set some point like this, that is we set a2 as a1 and b2 as p1, that is we are taking this interval, that is we are setting a2 as a1, that is a2 here, then after this stage this a1 is a2 and we call p1 as b2. So we are getting this interval, that is this is a2 b2. Okay, a2 b2. If f of p1 is greater than 0, f of p1 is greater than 0, but if f of p2 is less than 0, then we are setting a2 as p1, okay, a2 as p1 and b2 as b1. That is, if f of p2 is less than 0, if f of p2 is less than 0, then we are taking, we are considering this interval, that is f of p2 is less than 0, so we are setting a2 as p2 and b2 as b1, that is it is b1. Anyway, we are taking a new interval, bisected interval, that is a2 b2, with the condition that f of a2 is less than 0 and f of b2 is greater than 0. You have to set a2 and b2 so that this condition will satisfy, that is f of a2 is less than 0 and f of b2 is greater than 0. And also this interval is the length of this interval is half of the interval I1, so surely I2 is contained in I1. And what is the length of I2? I2 must be half of the length of interval I1. If we have I1 interval, length of the interval as b1 minus a1, then I2 has length 1 by 2 times b1 minus a1. So it is, I think it is clear. So we are getting, we have found, or we are constructed a new interval I2 which is contained in I1 and also has length 1 by 2 times v1 minus a1, and also this property holds, that is f of a2 is less than 0 and f of b2 is greater than 0. Continue the bisection process, that is first we are getting a1 b1, then if you are taking this, that is a2 b2, and next we are finding the midpoint of a2 b2, then if this is the midpoint, then we are setting a3 b3, like that it is going. So we are getting intervals I1 I2 I3 etc., for example ik, by successive bisection of the interval I, or I is equal to a1 b1, or I1 is equal to, I1 equal to a1 b1. We are getting these intervals with the property that one is contained in the other, that is I2 ik is contained in like that, subset of like that, I2 is a subset of I1. Okay, like this we getting a sequence of intervals, and also till this ik. After ik we can also do this bisection with ik is ak and bk, with f of ak is less than 0 and f of bk is greater than 0. So we take pk as the midpoint of this kth interval, that is 1 by 2 ak plus bk. So same case arise as we encountered with the when we bisect this a1 b1 interval. So here f of pk, same cases, that is f of pk may be 0, or f of pk is greater than 0, or f of pk is less than 0. If f of pk is equal to 0, you can set c equal to pk, then the proof terminates. That is, you have found a c such that f of c is equal to 0. But f of pk is not equal to 0. You have two cases, that is f of pk is greater than 0 or f of pk is less than 0. So as in the previous case, we have if f of pk is greater than 0, we put ak plus 1 as ak and bk plus 1 as pk. Okay, and also if f of pk is less than 0, then we put ak plus 1 as pk and bk plus 1 as bk. Okay, so we are getting new interval ik plus 1 as ak plus 1 bk plus 1. We have chosen ak plus 1 and bk plus 1 such that like this. So we have the property that f of ak plus 1 is less than 0 and f of bk plus 1 is greater than 0. That is, f of bk plus 1 is greater than 0. So we have a sequence of intervals I1, I2, I3, etc., ik plus 1, etc. So if we continue like this, the process will terminate at some point, locating a point say P1, Pn, such that f of Pn is equal to 0 and we are done. Okay, so if you continue this process, and it must be terminated at some point, because we are taking the midpoint of every interval. So at some point we will get, if the process terminates, then we will get a point Pn such that f of Pn equal to 0 and we are done. Okay, we have done with the proof. But if the process is not ending, no, it is not terminating, we can continuously choose this interval without terminating, then we get a nested sequence. Okay, nested sequence of intervals such that in is equal to an bn for every n closed and boundary interval. For every n belongs to n, we are getting this sequence of intervals, that is I1, I2, I3, etc., ik plus 1, etc. It goes on. We are getting this intervals with the property that these intervals with the property that f of an is less than 0 and f of bn is greater than 0, and also since these intervals we are getting by bisection of the previous interval, we can take the length of the interval as b minus a or b1 minus a1 divided by 2 raised to n minus 1. That you can check, okay, b minus a by 2 raised to n minus 1. It follows that by nested interval property, you have studied the nested interval property, that if the interval has a decreasing length, then there exists a point c that belongs to, there exists a point c that belongs to, it is by nested interval property. There exists a point if we are getting intervals like this, okay, if we are getting intervals like this and also its means length is decreasing, then we are getting a point, we must have a point c, c with which belongs to each in for every n, for every n. This is the nested interval property. We get a point c which belongs to every n. And also we have an is less than or equal to c less than or equal to bn, that we know because c is between an and bn, okay, for every n belongs to n. Then limit of bn minus an is equal to 0, which implies that limit of an is equal to limit of bn, and this is equal to c. So we have a limit of an and limit of bn as the point c. So we have sequence limit of an and limit of bn which is equal to c. And also we know that f is a continuous function. Hence limit of f of an is equal to limit of f of bn must be equal to f of c, since f is a continuous function. And also we know that f of an's are less than 0 for every n, therefore limit of f of an must be less than 0 for every n. And also f of bn is greater than 0 for every n, therefore limit of f of bn must be greater than 0 for every n. Therefore we get f of c, according to this f of c is less than 0 and also for every n, and also f of c is greater than 0 for every n. So we may conclude that f of c must be equal to 0. That means that c is the root of f. Hence we have the proof. So hence we have the theorem, that is c is the root of the function f. So we can conclude that we are getting a point c such that c is the root of f.